Hello everyone, and welcome to this video titled A Preview of Calculus. So in this video, I am going to be taking you through a sample version of a Knewton Alta assignment that is called A Preview of Calculus. So please understand that while I'm working through a preview version of the assignment, the assignment you do on your own, if you're a student who has to take these through Knewton Alta, you may be seeing different questions than I am, but the objectives are the same, and the way I'm going to be doing certain problems will be similar to the way you should be doing the ones that you're going to come across. Okay, so here we are, Knewton Alta. And you will not see the word preview. You're just going to see the name of the homework. So this one in particular is section 2.1, again called a preview of calculus. Upper right hand corner, you'll see a mastery bar that tells you how far along you've gotten in the assignment. Next to this is an activity log, which just shows you how many objectives there are in the assignment. So this one here has 2 objectives, and also your progress in each objective. So on the opening page here, you should be seeing the current objective. So here is preview the area problem by using rectangles to approximate area. Then you'll have a question related to that particular objective. And at the very bottom, you should be seeing a feedback button. So if you see any typographical errors, any issues with a particular question, or the solution to a particular question, you can send feedback directly to Knewton support, and hopefully they can fix things for you or assist you in some way. Now I will have this instructor cheat button. Obviously you will not have that as a student, but you will also have a more instruction button. So if you're working on a particular objective question and you don't remember exactly what to do, you can click on more instruction and it'll take you to further reading or videos or both related to that objective, and hopefully that will help you. All right, so let's get into it. So this first objective that I'm getting a question on is about the area problem. So let me explain that real briefly. So this is one of the big problems that we'll be tackling in a Calculus 1 course. So the area problem, here's the XY plane, and then suppose I'm given the graph of some function over some interval on the x-axis. So here's, say, x equals a, and over here, let's say, is x equals b. And then above this interval, I got, there's a point on some graph. Then above b here, here's a point. And then there's part of a graph of a function, over this interval. So here's part of the graph of, say, y equals f of x, over the interval from x equals a to x equals b. So what this area problem is about is, can we find how much space is taken up between the curve and the x-axis? This is the initial area problem. So the area, how many square units does this space take up? So this shape that I'm trying to find the area of in this picture, right, it's not a nice shape. It's not a rectangle, it's not a triangle, a circle, right? Things you would know the area of. So what we do is we estimate this area. We're going to approximate it using rectangles. So what's happening is the interval from A to B is broken up into pieces. So say I've got, 5 pieces here, and it doesn't have to be 5. And then in each piece, you can plug in a value from that piece. So say from this value A to this first value here, I plug in A, and it gives me this height. It takes me to the value on the function f of A. And then I create a rectangle with that height, and the width, is the length of this piece. So do you see how this rectangle here, the area of this rectangle I just made is pretty close. There's some missing stuff. I'm not getting all of it, but it's pretty close to, estimating the area under the actual curve. And then I could do the same thing in this next piece. I plug in a value, say this one here, takes me to the curve, gives me, the output for that input. And then I create a rectangle with that height and this width. All right, so this width, this height, and here's another rectangle. And again, you see the area of this rectangle is very close to giving me the area under, the original curve to the x-axis. And I keep doing this, plug in a value that takes it to the curve, input to output, and then create a rectangle with that height and that width. And do it one more time here, plug in this value, I get another height, and create a rectangle with that height. And then I'll plug in B here and get another rectangle. Now this one overestimates, but still, all these rectangles, if you were to add up all these areas, you're getting an approximation of the actual area under the curve. So that's all that's being done here in this initial section on, a preview of calculus. So if we look back at the problem, look back at the question. See, it's saying estimate the area between the x-axis and the graph of the function over the interval from, this is x equals 1 to x equals 4 by using the rectangle shown in the figure below. So the nice thing about this question is, they already did the rectangles for us, right? So here is the interval from 1 to 4 on the x-axis. And then you have this dark blue curve that's waving all around here. That's your function. We're trying to estimate, the area under this dark blue curve to the x-axis using the rectangles that are already shaded in for us. So hopefully you see that this shaded in rectangle area, is pretty close to giving me the entire area, the actual area under the dark blue curve. this area here is, there's a lot of missing space, but it's still an estimate. And then this third rectangle, kind of overestimates, it gives me more area than is actually under the dark blue curve, but it still estimates it. So then to estimate the area they want, you're just adding the areas of all these shaded rectangles up. So this first tall rectangle here has a height of 4 and a width of 1. So this is 4 square units. This second rectangle is just a 1 by 1, so there's 1 square unit. And this third rectangle has a height of 6 and a width of 1, so that's 6 square units. So I've got 4 square units plus 1 square unit plus 6 square units. Add all those up, and that's 11 square units that are shaded here. Okay, so the approximate area under the dark blue curve over the interval from 1 to 4 is 11 square units, right? So I'm entering 11 in the box here, and you see the approximately equal to wavy equal sign, right? Because again, the area is not actually 11 square units, but it's estimated to be 11. All right, so hopefully that made sense. Now, once you've entered an answer, you hit submit, and if you are correct, something green will come up and give you a confirmation that it was correct, and words of encouragement, keep it up. Now, after you've answered a question, so whether you got it right or wrong, you will see an answer explanation. I'd suggest you read through these, whether you got it right or wrong. Definitely if you got it wrong. Right? Read through these and hopefully you can figure out what went wrong and fix your mistake the next time you see a problem like this. And if you got it correct, maybe you did it in a way that is different from the way they did it, and maybe you like the way they did it better. And we'll, try that method the next time you see a problem like this. All right, so I'm going to continue on. All right, so I'm given another question. So they didn't change objectives on me. That does happen on occasion in Knewton Alta, where they'll be doing some interleaving and switching objectives on you. But I'm still in the same objective, this area problem, using rectangles to approximate area. And you can see now that my progress wheel on that objective is about a quarter done. The mastery bar went up a bit. Right now I'm 13% complete. And this is a pretty similar question. Estimate the area between the x-axis and the graph of the function over the interval from 1 to 4 again by using the rectangle shown. So once again, these shaded rectangular regions are estimating the area under the dark blue curve over this interval from 1 to 4 on the x-axis. So all we need to do again to get this estimated area, this approximate area, is just add up all these rectangles here. Now these all have a width of 1, so I just need to add them up. So there's, this first rectangle is a 1 by 7. So is this second rectangle. So that's 14, right? That's a 2 by 7 big rectangle. That's 14 square units there. And then I've got this 1 by 2 rectangle. So another 2 square units, right? 14 plus 2, 16 square units, right? So the area under that curve is approximately 16 square units. And I'll submit, and it is correct, right? Keep it up. Continuing on. All right, so you see how it did the switch? This is that interleaving. On occasion, it might change up. So it doesn't give me, 3, 4 questions in a row of the same objective. It'll switch to the other one. Okay, now this other one is preview the tangent problem by using secant lines and average rates of change. All right, so I want to talk about this tangent line problem a little bit first. So now we're on the tangent line problem. Okay, so here I'm going to do the same kind of picture as earlier. Got your XY plane. And then you're given the graph of some function, but not over a specific interval. All right, not right now. Just here's the graph of some function. Whoosh. All right. So here's y equals, say f of x. Now what the tangent line problem is I go to a specific value. So again, they're going to probably call this A in most texts. I plug it in, it takes me to this point here on the curve. Okay, so here's a point on the curve with x coordinate A, and then the y coordinate would be, the value of f at A, so A comma f of A. So the tangent line is the line that goes through this point. So if I want the tangent line to a curve at a point, it's the line that goes through that point, but also, is tangent to the curve. That means it points in the same direction that the curve is going in at that moment. All right, kind of like the tangent to a circle, right? If you recall circles, if you took a point on a circle, a tangent line just touched that one point of the circle. Okay, so a tangent line at a particular point on a curve, again, it points in the direction that the curve is going in at that moment. So here's the problem, right? The tangent line problem in calculus. We're going to try to find the slope. And what is that direction that the curve is going in at this moment, right? And so remember, the slope of a line will indicate the direction you are moving in. So we're trying to find the slope of the tangent line. Now I noticed that this slope of the tangent line in this text, in the instruction you'll see here in Newton, it's going to be represented here in the preview of calculus section by this m. Remember m for slope, y equals mx plus b, right? M usually represented slope. And then you have this subscript of tan for the slope of a tangent line. Now here's the big issue with this. I know that this point, this a comma f of a, is on this line. But remember, to find the slope of a line, you need 2 points, not just one. So this is tough, right, at the moment. So what we do, how this is calculated, this slope of the tangent line, is we use other lines that are close to this line to estimate the slope of the tangent line. Kind of like how in the area problem, we took areas of rectangles, things we know how to find the area of, to estimate the area under the curve. So we're going to take other lines that go through this point that are close to this tangent line to help us estimate the slope of the tangent line. So to do that, we're going to pick, choose a value. So here's some value called x. that is not the same as A, right? That's key here. Okay, so because if this were A again, I'd only be at the 1 point. So I go to X, I plug it in, and it takes me to my function, right? There's the point on the curve. Here is the point with X coordinate X and Y coordinate f of X. And I'm going to draw a line. Now I have 2 points on the curve, this AF of A and XF of X. Remember, when you have 2 points, you can draw a line. Right, so here is a line going through those 2 points. So through AF of A, and XF of X, right? So this line I just drew here. Now this line that is cutting through the curve, that line does not point in the direction the curve is going in at the moment. So it's not a tangent line, right? If it's cutting through a curve, it's referred to as a secant line, right? Cuts through 2 points. So secant line. Just like with circles, right? Remember for circles, it's got a similar definition. A line was tangent to a circle when it hit just 1 point. And another line, any line that cut through the circle, was called a secant, right? So it's kind of similar to that, those terms there from geometry. Well, do you see how the secant line is an estimate of the tangent line? Right? So the slope of the secant line that I just drew line, L-I-N-E, this will be represented by M with a subscript of SEC for secant. The slope of this, orangey line, this secant line I made cutting through 2 points, is an estimate of the slope of the tangent line. All right, so I'll write that up here where you have the slope of the secant line, okay, is going to be approximately, and not exactly the same as the slope of the tangent line that we're looking for, right? So this is big. All right, this is the initial part of our, getting toward the slope of a tangent line. All right, so what is this slope of the secant line? So I'm going to keep the picture up here, put up another, we'll overlay another piece of paper here, sorry. So slope of the secant is approximately slope of the tangent. Again, the slope of this secant line remember how to calculate slope. It's change in y over change in x, right? So I've got, these 2 points here. Right, we've got the line. It's a line with points a comma f of a and x comma f of x. So I take, remember the change in y, subtract the y coordinates. That's going to be the numerator of the slope. So f of x minus f of a divided by, and then the change in the inputs, the change in x, so x minus a. Okay, so this is one expression for the slope of the secant line. And again, this should be approximately the same as the slope of our tangent line. And to get it to be better and better, because like the line I have drawn here doesn't look that close to the tangent line. But if I want my line to be a better approximation, I just move x towards a. Say my x was here instead, even closer to a. Well, then the xf of x point would be here, and my secant line would be a lot closer to the tangent line, right? There's another secant Now this is getting a little cluttered. I'm going to go to a new page, but in that case, when the value I choose is closer to A, the secant line is much, much better at approximating the tangent line. So I'll keep this in a box. Right, this is one way to express the slope of a secant line, and then use it to, help you estimate the slope of a tangent. We'll get to that with some problems, in a minute. Now, another way to express the slope of a secant line, right, you might see this as well. So, and I'll draw a similar picture to earlier. So again, you got the graph of some function. Right, there's a y equals f of x. And we're looking at a particular value, called a. So here's the points on the graph, a comma f of a. And here's my tangent line, right? Again, it touches just at that point and, points in the direction the curve is going in at that moment. All right, so here's my tangent line. I'll just put tangent. So another way they can express this that you're going to see is, again, I want to use a secant line, some line going through 2 points on the curve that are close to this tangent line. So I take a value that's, again, not the same as a, but is, a plus h, right? So this h value is the run, right? The change, h is the horizontal change, h for horizontal. So I go from a to, I add h or subtract h from it. I'm on either side of a. I go to a plus h, plug that in, and I get another point on the curve with, input a plus h, output f of a plus h, and then here's our secant line, again, going through this point and then this other point, right? So here's our secant, and in this case, the slope of the secant line is the change in y, right? So it's the value of f at this a plus h input minus the value of f at a, and then all divided by, and then a plus h minus a would just be h. Again, h here is the run. It's going to be the denominator of the slope in this case. Once again, this should be approximately the same as the slope of the tangent line. Right, so here's another way they'll express the slope of a secant. All right, and then one more thing. It's a lot of letters, a lot of stuff here, a lot of pictures with just letters and no numbers. But one more thing that was in the title of the objective. There's a big difference between average rate of change and instantaneous rate of change. So let's write up what those are here. So average rate of change. This is the average rate of change. This is over an interval. Okay, this is how much does y change when compared to the change in x over some interval on the x-axis. This is the slope of your secant lines. All right, so the slope of so like here, this secant line I drew, the slope of this line would be called the average rate of change of our function from a to a plus h. Or back here, this orange secant line, the slope of this line would be called the average rate of change of our function from a to x. All right, so it's over some space, over some interval on the x-axis. Whereas the instantaneous rate of change, of a function This is what happens not over an interval, not over a big space of the x-axis, but what happens at one value at a particular point. Where is the curve moving at a particular point? How much is y changing when compared to x at a particular point? So this is at a point, right? At a single point, at a single value. And this is the slope of your tangent line, all right? So when you see the word instantaneous come up, think slope of tangent at a single point. When you think average rate of change, or when you see average come up, talk about the average velocity, average rate of change of a function, whatever. Think the slope of a line going through 2 points on a curve, over some interval. One at, a, one at a plus h, or one at a and one at b, but it's over an interval. So hopefully that makes that average rate of change should be something you saw in algebra or pre-calc before anyway. The only thing that's really new here is this instantaneous rate of change, the slope of a tangent. Okay, so finally, back to our problem. So look, this question is the position of a bottle rocket in meters is given by this function here. So instead of x, the input is t, right? And instead of y or f, the output's called h. No different though. Okay. So h of t equals -3 times t squared plus 36t plus 400, where t is measured in seconds, so t is time in seconds. And again, h is height in meters, position in meters, off the ground of this rocket. Whereas to compute the average velocity of the bottle rocket over the time interval from 3 seconds to 6 seconds. So I said this earlier, right? The average rate of change of a function is always over some interval from some beginning point to some end point. So from t equals 3 to 6 here. So average velocity, right? That's your change in position divided by change in time. Right, so I'll write that up. Right, so here's our function. Again, h of t is -3 times t squared plus 36t plus 400. And this is this is position in meters, height off the ground. Let's put m for meters. I'll write the word meters because I used m for slope earlier. And then t is representing time, how much time the rocket's been in the air in seconds. Now we could look at a graph of this, right? So you don't have to do this, but I'll go to this. There's a website called Desmos, DESMOS.com. Here it is here. And it's a great free online graphing calculator. And if I go, enter the function as they gave it to me, h of t equals -3 t squared plus 36t plus 400. Oops, move the cursor. Plus 400. Now, I'm hoping you know enough about quadratic functions to know that this is a parabola opening down, right, with an initial height of 400, right? When t equals 0, this should be starting off here at the point 0, 400. Right, you can maybe see that here. And then the rocket, goes up to a certain point and then comes down, right, hits the ground eventually. So I'll make a rough sketch of this on my paper. So again, here's your time in seconds, and then the height off the ground, and when time is 0, you got 400, there's 0, 400, and then it shoots up, eventually reaches some highest height and then comes back down, hits the ground at some point. Now, the big question is, they're saying what's the average velocity? Right, so AVG for average. From t equals 3, so 3 seconds, to t equals 6 seconds. So average velocity, again, average rate of change. This is going to be how much the height changes, right? The change in output, delta H, divided by how much the time changes, right? So delta T, or delta for change. And in order to calculate this, then I plug in 3, so 3 seconds. That'll give me some output. So here's, 3 comma H of 3. And then I plug in 6. Now knowing what I know about quadratics, the opposite of b, negative 36 over 2a, that'd be negative 6. Negative 36 over negative 6 is positive 6. That's where the highest point of the rocket's going to be at, is when it's, 6 seconds later. But anyway, I plug in 3, I plug in 6, you got 6 h of 6, and the average velocity is the slope of this line, right, which is a secant line. So again, this is the slope of a secant line, which I'm going to be taking the value of h at 6 minus the value of h at 3, and then divided by 6 minus 3, right? And the change in the height divided by the change in time. Now I could go through and plug in 6, plug in 3, but I'm at home, I'm working on homework. I don't want to waste all that time, right? Doing arithmetic. So I'm going to do it on a calculator. All right, what is h of 6? So that's 508. What is h of 3? That's 481, right? So again, I'll have the calculator do all this for me, but we end up here with, it was 508. So, 6 seconds in, you're 508 meters in the air. Whereas 3 seconds after the launch, you were, 481 meters in the air, right? So if I subtract those, that's, 27. I can do that on your calculator for that. So the height, from 3 seconds to 6 seconds, the height increased by 27 meters. So that's the change in height. And then the change in time is simply, 3 seconds. And 27 divided by 3 is 9. Now the units on this, and the change in height, those were in meters, right? So you have meters in the numerator. Changes in time will be in seconds in this. So this will be in meters per second, which is, what a velocity typically is. It's a change in position over change in time. Distance units over time units, and there we go. This is what they're asking for. The slope of this secant line, the average rate of change from 3 seconds to 6 seconds. How much did the height change when compared to the time change, in that interval? So I go back to the problem, and that's all they're asking me to enter, right? The velocity average, right? So V for velocity, and then they got AVE here for average. And according to my calculations, right, the average rate of change, the average velocity of this rocket over that time period from 3 to 6 seconds is 9 meters per second. Submit. That's correct. All right, again, read through, please, the answer explanations. Make sure you understand what's going on, and we'll continue. All right, so not a lot of progress there. I think it's because there's a lot of different types of questions in this particular objective. So you'll see after I get a few right in a row that the progress will move up a bit faster. So it starts off barely moving up on that objective. But again, like some objectives have several different varieties of question. So they kind of want to get you through all the varieties of question before they really understand, they know that you're mastering stuff. So the progress doesn't move up as fast as you'd like it initially. But usually it'll take 4 or 5 questions correct in a row to get, a full completion of a particular objective. All right, so there's another one from that, preview the tangent problem by using secant lines and average rates of change. So this one, you got the position of a ball in meters dropped from a 409 meter tall building is given by the function, s of t. So s of t, s represents the position, the height in meters off the ground. And t is time, and it looks like time in seconds again. All right, because they got meters per second in the answer. So s of t equals negative 5t squared plus 409. Find the average velocity of the ball over these two intervals. And then use this information to approximate the instantaneous velocity of the ball at 2 seconds. So notice the word instantaneous showed up, and it was only at a particular value. It's not from 2 seconds to 4 seconds. It's at 2 seconds. What is the speed or velocity of this ball? So again, we're going to use some secant line slopes to estimate, get an approximation of the tangent line slope, the instantaneous rate of change. All right, so once again, I'll start writing this stuff up, and then we'll go to Desmos, take a look at some things. So my function here is, s of t equals negative 5 times t squared. So once again, we got a quadratic that's going to be a parabola opening down here, plus 409. If I were to graph this, again, time in seconds, and then s is the height now off the ground. At time 0, you have it said it was dropped from 409 meters, right? So time 0, 409 meters. And then, this has a 0, 409 would be the vertex, and then your parabola is doing this, right? It's dropped and eventually hits the ground at some point. So you got part of a parabola. And we can see that more, maybe it's a little nicer in Desmos. So here's, s of t, I'll just put it in as they gave it to me, equals negative 5t squared plus 409. And you can see this, 0, 409 at the top here, parabola opening down, and again, eventually hitting the ground, there's where it's hitting the ground around here somewhere. All right. But we're concerned with when t equals 2. So what's s of 2? All right, so it's 389. All right. So if I were to plug in 2, so yeah, maybe I'll go over here and make this a little bigger. So we got this parabola, and it's doing this. Things falling, right? I'm taking this over here. So I'm going to plug in, so say this is the t-axis right down here, and I'm going to plug in 2, because they asked about the instantaneous velocity at 2 seconds. So here's a point, there's 2, comma, and then I just plugged in 2 in Desmos there, right? So negative 5 times 2 squared, it's negative 20 plus 409 would be 389. Right? So at 2 seconds, this ball is 389 meters in the air. So I got the point 2, comma 389 on the graph, and they want us to estimate the slope of the tangent line. So here's the line that has that point on it, going in the direction that the curve is. And the slope of this line, right, the slope of the tangent line is this instantaneous velocity, v inst, that they got there. So again, the problem is the same problem I mentioned earlier. I cannot find the slope of a line with one point on it. So that's why they're having you use some other values around 2. So you see from 1.999 to 2. Oh, sorry, I didn't go to the problem. So here's back at the problem. So you see how they're having you use values close to 2, but or near 2, but not 2 itself. So you see, if you take the average velocity, you take the slopes of the secant lines from 1.999 to 2 and 2.0 to 2.001, and use those slopes to estimate the slope of this tangent line, this instantaneous velocity. So let's say 1.999 is here, right? That'd be to the left of 2. So I got a point there. So here's a 1.999, and then, S sub 1.999. I'll just have the calculator do that for me. And then here's a secant line, right? Going through the point to 389. There's one of the secant lines we'll be using. And then the other one is at, they said they use the other one from 2 to 2.001. So I plug in 2 point, that takes me to some point to the right of this point. Here's 2.001, comma, S of 2.001. And then here's another secant line, right, going through our point to 389, and then this other point here. So here's another secant. See how both of these secants should be, approximations of my tangent line. All right, so I'm going to find the average velocity, slope of the secant line on that interval from 1.999 to 2 that they asked for. So this is, the value of S at 2 minus the value of S at 1.999. All right, there's the change in output divided by, and then the change in time is 2 minus 1.999. So 1,000th of a second will be in the denominator here. So this slope, so I'm going to have a calculator do this for me. So I'm just going to go, what's, put this in parentheses. So what's S at, so I already have S at 2 there, and minus the value of S, the height at 1.999 seconds. So that's how much the height changed. All right, it's very tiny change. So you see how it's negative 0.019995. So in 1,000th of a second, the ball dropped, 0.19995 meters, right? Very small drop. And then what's the rate of change? I divide by 2 minus 1.999, right? So here is the slope of that one secant line. So it's this one here, from the point where the time is 1.999 and the time is 2, that line has a slope of, negative 19.995. This is negative 19.995 is the slope of that secant line. I'm going to do the other one. All right, they also asked us to use the slope of the secant line from, time 2 seconds to 2.001 seconds. So again, this is going to be the change in output. So what's the height at 2.001 seconds minus the height at 2 seconds, and then I divide by the change in time. 2.001 seconds minus 2 seconds, and again, this is going to give me some value that I'll have the calculator do for me. So I'm just going to change some of this. So we got S at, 2. 0.001 minus the value of s, the height at 2, and then divided by the change in time, 2.001 minus 2. And it's got a slope of negative 20.005. Okay, so this line here, from the point where time is 2 to the point where time is 2.001, this line has a slope of negative 20.005. So if you look at these, negative 19.995 and negative 20.005. This line has a slope of negative 19.995. This line has a slope of negative 20.005. You see how the tangent line is between those? All right, the tangent line at 2 is between these. And they're saying round to the nearest whole number or nearest integer. So I would guess, so from these, I would guess that this slope of the tangent line, the instantaneous velocity, is about negative 20. All right, that's between those. And of course, this would be meters per second. All right, so the speed, the velocity of the object at that moment, that one moment, the instantaneous velocity, based on those two secant line slopes, I would say is about negative 20 meters per second. And that's what you're going to be entering, right? That's what they're asking for. Round to the nearest integer, the negative 20 if necessary. So velocity, negative 20, instantaneous velocity, negative 20 meters per second. Great. So again, please read through, all right, see how they found the slope of the secant line, the average velocity from 1.999 to 2 seconds. Then they did the same from 2 seconds to 2.001 seconds, found the average velocity. And then they're like, hey, the tangent line, the instantaneous velocity must be somewhere between those, probably around negative 20 when you go to the nearest integer. Wonderful. All right, so back to the easy one, the area problem. So this is no different than earlier. It's a different interval. This is once again estimate the area between the x-axis and the graph of the function over the interval from negative 1 to 4 by using the rectangle shown in the figure below. So it's just once again adding up shaded areas, right? The shaded areas of these rectangles under the dark blue curve. So I've got, a 5 by 1, a 6 by 1, a 1 by 1, another 5 by 1, another 6 by 1. So that's 11, 22, 23 of these square units are shaded in. So that the area under this dark blue curve, over the interval from negative 1 to 4 is about, it's approximately 23 square units. And that's all I'm filling in here, 23. So this is just a matter of counting shaded boxes. Hopefully that's easy enough. Continuing on, so it looks like, see, I'm pretty much 3/4 of the way done with this one, so hopefully this is the last one from these. These are pretty easy. So this is over the interval from negative 1 to 3, right? What's the approximate area? So again, I got a 4 by 1, 2 by 1, 2 by 1, so that's 8 there, and then a 6 by 1, 8 plus 6 is 14. So the area under that curve over that interval is approximately 14 square units. So I'm typing in 14 there. All right, cool. So once you've completed an objective, it'll tell you how many more you got to go, right? So that's 1 of 2. All right, so you see how after I got that second question right from the average rate of change and tangent problem objective, the progress barely went up earlier, but now it's about 1/5 of the way, 1/4 of the way, right? It went up a little more than it did the first time. All right, so let's go look at this one. All right, so this one's having me fill in a table. Now these will be slopes of secant lines. All right, these will be slopes of secant lines. And I'll show you a way you can express we can just express the slope of a secant line in general and make a table for it. So here we got a function, some quadratic again, f of x equals 5 minus 3x squared. And we're asked to use a table to estimate the slope of the tangent line to f at the point 0, 5. Find the slope of the secant line PQ for each point Q with the x values given in the table. And you're asked to round each of these to 6 decimal places if necessary. And then use the answers to estimate the slope of the tangent line at point P and round your answer to the nearest integer. All right, so whole numbers. So here's the picture. All right, again, our function. So here's the function we're given. It's 5 minus 3x squared. Once again, another quadratic, right? So if I were to graph this, x-axis horizontal, y or f-axis vertical. This would have 0, 5, right? And they mentioned that, right? Here's the point, 0, 5, and it'd be a parabola opening down, and the vertex would actually be 0, 5, right? So some parabola opening down like this. Now, you're going to see this later in the course. But at points like this, where you're at the top of a hill, the top of a curvy hill like this, the tangent line, is horizontal. So I already can tell you that the slope of the tangent line there is 0. So I'm going to put that in later. But we're going to see, all right, because remember, horizontal lines have a slope of 0. Now, what we're given is this table, right? So this is called point P, right? They call this point P. And what they give us are a bunch of x values for these other Q points. So the x values we're given are around 0, right? The x value of 0, 5 is 0. We're given all these 4 x values around 0. So here's 0. All right, we got the point 0, 5. I'd like to estimate the slope of this tangent line. So we're plugging in values around 0. So to the left, they got, negative 0.01. So I'm going to get that point. So this is one of the Q's. And here's, a secant line. We're going to find the slope of that one. And then they do the same for, negative 0.0001 is another one, right? Even closer to 0. So I plug that in, get this. Here's another one of the Q points. And here would be the secant line there. Right, another secant. Going to find the slope of that one, right, and fill it in the table. And the same thing on the other side. They give us positive 0.01 is the x, so that'll give me a point over here, and it's symmetrical and all that. And so here would be another secant line, right, through P. So this is another Q point. So there's another secant, and then go even closer again. Here's a positive 0.0001. They're plugging that in. And that'll take me to, say, this point here, and there's another Q point, and I want the slope of this secant line as well. So there are 4 secant lines that I'm going to be finding the slopes of. Now, rather than, you know what, I will just do this. All right, so let's do the secant line from negative 0.01 to 0. All right, with that value. So I'm going to find the average. So the slope of the secant line, the average rate of change, again, it's going to be the value of f at 0 minus the value of f at negative 0.01. There's your rise, and then divided by, 0, minus negative 0.01, right? So that'll be positive 0.01. Right. So I'm going to just go to the calculator for that. So I'll go to Desmos, enter this f of x function. All right, here's what we were given. 5 minus 3x squared. So again, the parabola, this is the picture I drew earlier, right, with the 0, 5 on top. And I want to calculate, again, the slope of the secant line from x equals, negative 0.01 to 0. So f at 0 minus f at negative 0.01. And then all this divided by, the change in x is 0 minus, negative 0.01. All right. So that slope is, so that's this line here, okay? That's this line here. So this line has a slope of positive 0.03. And that's what I'm going to be entering in the table. Because again, they want the slope of PQ, the slope of these sequence lines. So when x is negative 0.01 to 0, the slope of that line was positive 0.03. And I don't need to go to 6 decimal places for that. All right, it stops at 0.3. But if it went like beyond, 6 decimal places, I would round it to 6 decimal places. That's what they're asking for these slopes. All right, so I'm going to do the same thing. So again, this slope is 0.03. And then this line, when I'm going from negative 0.0001 to 0. Right? So the slope of the secant line there, again, is the value of f at 0 minus the value of f at negative 0.0001 divided by, and then 0 minus negative 0.0001. All right, just change an output over change an input. So all I'm going to change in my calculator there is those values. So back on Desmos. So I'm just changing this from negative 0.01 to negative 0.0001. Same thing down here. Add 2 zeros. So now the slope is 0.0003. So that's what I'm going to enter here in the table for the negative 0.0001. Positive 0.0003. And that doesn't go beyond 6 decimal places, so I don't have to round. Let's double check that. Yeah, 0.0003, right? So that's this line here. Right, that's this line here. The slope of that line is 0.0003. Right. So you see that as the point gets closer to P, right, as these Q points get closer to P, I can tell that the secant line slopes are getting closer to 0, right, 0.03 and then 0.0003, right? The slopes are getting closer to 0, which I already kind of told you, right? The slope of this tangent line is 0. These will get closer and closer to 0. All right, now how about this one? All right, so I'm going to go from 0 to positive 0.01 and the slope of the secant line. I'm going to do f at 0.01 minus f at 0 divided by 0.01 minus 0, right? So again, that's the slope of this line here, right? Through that point where x is 0.01. So back to the calculator, the f at, well, actually, I can do the other way around where at f of 0, I'm just going to change this to positive 0.01 and then this to positive 0.01. As long as those differences are taken in the same order. And now you see a line with a slope of negative 0.03. All right, so that's going to go down here with 0.01. The slope of the secant line is negative 0.03. And back on paper, right, that would be this line here, right? Slope is negative 0.03. And then, and being symmetrical, I'm going to guess that this slope is negative 0.0003. All right, because when I go from 0 to 0.0001, this secant line here and so 0 to 0.0001. The slope of the secant line, and I'm going to do f at 0.001, 0001 minus f at 0 divided by 0.0001 minus 0, or switch those, which I'm going to be doing. Right, as long as they're taken in the same order. So here's, f of 0 minus f of 0.0001, and then divided by 0 minus 0.0001, and you're seeing a slope of negative 0.0003. Right, so I'm going to enter here. All right. So once again, based on all these slopes, you see how when x gets closer to 0, the slopes of these secant lines are also getting closer to 0. All right, so the slope of the tangent line, I would say, is approximately 0, right, around the nearest integer. And these are all getting closer to 0 as x gets closer to 0. So submit. Hooray. All right, so a lot of work there. Still manageable with definitely, I would definitely pull Desmos or some calculator for these. Let me go through all that. Yeah. And I do like the way they're doing this here. So I'll show this to you next time, where I just enter an expression for the slope of a secant line with x involved and just make a table for that. I'll be a little faster. And this is, all right, so this is just what's the slope of the secant line between x equals 2 and x equals 3. Again, slope of a secant line is one of those average rates of change, which will be over an interval from one value to another, right? Again, instantaneous is at one value, average is, between two from one value to another over an interval. So find the slope of the secant line between x equals 2 and x equals 3 for the function given here. Enter your answer in either exact notation or round to 4 decimal places. So write out the function. So here's f of x equals, you got x squared plus 4 divided by negative 2x plus 2. And we're trying to find the slope of the secant line, right? The average rate of change on the interval from x, it said x equals 2 to x equals 3. So again, this is just your average rate of change. It's just going to be what's the value of f at 3 minus, what's the value of f at 2. So that'll be your rise, change in y, and then divided by 3 minus 2. All right, so it's just what's the value of f at 3 minus the value of f at 2. Okay, now these shouldn't be too bad. When I plug in 3, f of 3, you got, 3 squared is 9, 9 plus 4 is 13, divided by, and then negative 2 times 3 is negative 6, plus 2 is negative 4. So it's negative 13 fourths, then minus, and then f at 2 is 8, 4 plus 4 in the numerator, and then plug in 2 down here, you got negative 4 plus 2 is negative 2. So this is negative 4, which, if I'm going to get common denominator here, that's negative 16 fourths. So negative 13 fourths for f of 3 minus, negative 16 fourths for f of 2. And then you divide by 3 minus 2. 3 minus 2 is 1. So I really don't need to write that. Divided by 1 doesn't do anything. And so I'm left with negative 13, plus 16 fourths. So that's positive 3 fourths, or 0.75. Which again, you could have also gone to Desmos and done this, right? Had Desmos do this for you. I plug in the function. We got f of x equals, now make sure you're putting numerators with multiple terms in parentheses, right? So it's all in the numerator. We got x squared plus 4 divided by, and then this negative 2x plus 2. And all we want is the value of f at 3 minus the value of f at 2, divided by 3 minus 2. I know 3 minus 2 is just 1. But it's 0.75, which when you change to a fraction here is 3/4, right? You can do that with some values. So I can put in 3/4. I can put in 0.75. I'll just put in 0.75 as the slope of that secant line, right? The average rate of change. Great. And then it looks like it's filled in there. So when I hit continue, should be all done. Those were the only two objectives. So the assignment is, complete, or at least the preview is complete. But, your assignment when you're working on it, it'll be pretty similar to this. You might get different looking problems, you might get different functions, some different numbers, but the way you go about doing them would be the same. All right, so hopefully this helps you when you're working through the assignment on your own. And thank you very much for watching.